Hello. Hello. Is it audible?
Yes, sir.
Now let us start. Today we will discuss on this ideals and Rees congruences. Ideals and Rees congruences. Okay. So we know that in ring theory or in any other, say for example in group theory, there is a close connection between morphisms and ideals. But the same is not true in case of semigroups. So we know that in ring theory, there is a close connection. There is a close connection. हाँ ये म्यूट कर दो भाई अपनी आवाज किसने ऑन की है? There is a close connection between ideals and morphisms. Between ideals and morphisms. What is that actually? We know that suppose I have a ring R and a ring say R dash and I have a morphism from say F from R to R dash, then I have kernel of I is an ideal. Kernel of F is an ideal in R. And if I have an ideal in R, suppose I is an ideal in R, so I can construct the quotient ring R by I, and I have a morphism from R to R by I. That is the natural map. So there is a close connection. You can say there is a one-to-one correspondence between ideals and morphisms. Given a morphism, you can construct an ideal, and ideal is nothing but the kernel of that morphism. And given an ideal, you can have a morphism from R to R over I, the quotient ring. So that's why I'm saying that in ring theory, there is a close connection between ideals and morphisms. However, so the corresponding link in semigroups is not that satisfactory. The corresponding link between the corresponding link in semigroups is not that satisfactory. However, there are some morphisms which we call as Rees morphisms in semigroups that are closely connected to ideals. However, there are Rees morphisms in semigroups that are closely connected to ideals. that are closely connected to ideals. Okay, so how these morphisms are connected to ideals? So let us elaborate that. So let I be a proper ideal of a semigroup S. Let I be a proper ideal of a semigroup S. Let us take this relation rho I. Rho I is what? Rho I is you take it as I cross I union identity relation on S. Okay, so it's a relation on S basically. Then we claim that rho I is a congruence on S. Then rho I is a congruence on S. So to show that it is a congruence, first it must be an equivalence relation. So reflexive. Since IS is a subset of rho I, so it is clearly reflexive. So it is clearly reflexive. It is clearly reflexive. So it is clearly 1 minute. So it is clearly reflexive. Just 1 minute. So it is clearly reflexive. It is clearly reflexive. Now symmetric. So let x comma y belong to rho I. So by definition of rho I, x comma y belongs to I, because rho I is I cross I union identity relation on S. So either x comma y belong to I cross I, or x comma y is here. So this is what I'm saying. Either x y belongs to I, or x is equal to y, which implies that y comma x belongs to I, or you can say y is equal to x. And this is nothing but it says that y comma x belongs to rho I. So it is symmetric. It is symmetric. Now transitive. So let x comma y belongs to rho I, and say y comma z belongs to rho I. So x comma y belongs to I, or x is equal to y, and y comma z belongs to I, or y is equal to z. So we have different cases here. So first case is that suppose you have x comma y belongs to I, and here you have y comma z belongs to I. X comma y belongs to I, and y comma z belongs to I. So this actually means that x comma z belongs to I. So this means that x comma z belongs to row I. So the result is true in this case. Second case could be x is equal to y and yz belongs to I. Now see, x is equal to y and yz belongs to I, and it says again that x comma z belongs to I, and this says that the pair x comma z belongs to row I. Case 3. So we have taken all the choices with x comma y belongs to I. We have taken these two cases, x comma y belongs to I, and yz belongs to I, and then x is equal to y and yz belongs to I. Okay, now take these two cases. Case 3 is x comma y belongs to I and y is equal to z. X comma y belongs to I and y equal to z, this one. So x and y, they are in I and y is same as z, and this says that xz belongs to I again, and you get that x comma z belongs to row I. And the last case is that x is equal to y and y equal to z. X is equal to y and y equal to z, and this means that x is same as z. So you can say that x comma z belong to is, and which is a subset of row I. So in all the cases you have the transitive property. This shows that row I is equivalence. This shows that row I is equivalence on S. Now it should be compatible also. So let also let x comma y belong to row I and say some z belongs to S. So this means x comma y belong to I, or x is equal to y and z belongs to S. Now see here, I is an ideal. So you can just say that xz comma yz belongs to I, or xz is equal to yz, and this says that the pair xz comma yz, it belongs to row I. So this means row I is right compatible. Right compatible. Similarly, we can show that row I is left compatible. Similarly, row I is left compatible. Row I is left compatible. So thus row I is a congruence on S. So once you have a congruence on a semigroup, you can take the quotient semigroup as our row I. So hence we have the quotient semigroup. Hence we have the quotient semigroup. Quotient semigroup as our row I. Now, what is this as our row I? How do the elements of row as our row I they look like? So note that S over rho I. S over rho I is nothing but it has only two choices. Any class, because the elements of here are actually rho I classes. So any rho I class is either whole I or it consists of singleton elements, singleton x, such that x belong to S minus I. This is actually by its definition. Because what is your rho I? Rho I is actually I cross I. I cross I union 1s. तो आप कोई भी एलिमेंट चूज करेंगे, किसी एलिमेंट की क्लास, सो कोई भी एक्स वाई लेंगे आप रो आई में, कोई भी पेयर आप एक्स का वाई लेंगे रो आई में, या तो दोनों आई में होंगे, दोनों आई में होंगे, या फिर एक्स इज इक्वल टू वाई होगा। अगर आई में नहीं होंगे तो एक्स इज इक्वल टू वाई होगा, तो उस केस में ये सिंगलटन होगा। फिर अदरवाइज जो है वो क्लास पूरी आई के बराबर होगी, बिकॉज ईदर एक्स वाई बिलोंग टू आई और x is same as y. This is the definition. So, so this S over rho I is actually this I union singleton x such that x belongs to S over I, S minus I. Okay, so that is to say that S over rho I consists of I together with together with elements of S minus I, together with elements of S minus I. Okay. Also, if I take any two elements in S over rho I, so suppose I have Z, W, they belong to S over rho I. तो क्या होगा आपके पास, या तो Z इज इक्वल टू W इज इक्वल टू I होगा, और Z होगा कुछ सिंगलटन X एंड W होगा कुछ सिंगलटन Y, where your elements X and Y they are elements of S minus I. ठीक है। तो जेड डब्ल्यू का अगर आप प्रोडक्ट लेंगे, इफ यू टेक द प्रोडक्ट जेड डब्ल्यू या तो आई होगा, और या फिर ये प्रोडक्ट जेड डब्ल्यू जो होगा वो कोई सिंगलटन होगा, क्योंकि प्रोडक्ट तो इसी में बिलोंग करेगा एस ओवर रो आई में ही। या तो जेड डब्ल्यू फिर आई होगा, या जेड डब्ल्यू कुछ सिंगलटन टी होगा, सॉरी इट वुड बी सिंगलटन टी, वेयर टी बिलोंग्स टू एस माइनस आई। ओके, ओके। सो अगर जेड डब्ल्यू अगर जेड डब्ल्यू सो in S over rho I, the product of in S over rho I, the product of in S over rho I, the product of any two elements is same as their product in S if it lies in S minus I. Otherwise, the product is I. Otherwise, otherwise the product is I. तो प्रोडक्ट जो है वो सेम होगा जो उनका एस का प्रोडक्ट है, जो उनका प्रोडक्ट एस में है, वो जो उनका प्रोडक्ट एस में है, क्योंकि जेड डब्ल्यू तो सिंगलटन टी है, सिंगलटन टी उनका प्रोडक्ट एस में ही है। अगर ये प्रोडक्ट एस माइनस आई में लाइक करता है तब, अगर ये प्रोडक्ट एस माइनस आई में लाइक करता है तो ये प्रोडक्ट सेम होगा जो इनका प्रोडक्ट एस में है, अदरवाइज प्रोडक्ट होगा आई के बराबर, अदरवाइज द प्रोडक्ट इज आई। all if now see here, if z belongs to s minus I and w belongs to I, then what about zw? Zw belongs to I. Zw belongs, because this is an ideal, because I is an ideal. I is an ideal. Okay. इसी तरह wz also belongs to I, because I is an ideal. I is an ideal. And what is w product w? W product w जो है, because w is I and it is actually I product I which is contained in I. Okay. So what I am saying here is that this I behaves as the zero of S over rho I, because you take any element Z and take multiply this with W. W is actually the zero. है ना? So this, what is S over rho I? S over rho I is basically I union singleton x such that x belongs to S minus I. तो किसी भी एलिमेंट के साथ इसका प्रोडक्ट जब आप कर रहे हैं तो वो प्रोडक्ट आई ही आपको मिल रहा है, जेड डब्ल्यू आपका आई में ही है और डब्ल्यू जेड भी आई में है, और जीरो मल्टीप्लाइड बाई जीरो भी आपको जीरो ही मिल रहा है। सो सो आई बिहेव्स एज ए जीरो ऑफ एस ओवर रो आई, एस ओवर रो आई। ओके, so we can think of, so we can think of this s over rho I as s minus I union 0, where all products not falling in s minus I are 0, where all products, क्योंकि मैंने पहले ही कहा या तो प्रोडक्ट s माइनस आई में होगा या प्रोडक्ट यहाँ होगा, अगर s माइनस आई में प्रोडक्ट नहीं होगा तो फिर 0 होगा, फिर where all products not falling in s minus I are 0. Okay, so this is what, so to sum up the discussion, अगर आपके पास I कोई प्रॉपर आइडियल है, I इज ए प्रॉपर आइडियल, तो किसी सेमी ग्रुप S का प्रॉपर आइडियल है I, तो आप एक वहां पे कॉन्ग्रेंस कंस्ट्रक्ट करेंगे I क्रॉस I यूनियन आइडेंटिटी ऑन S, देन यू टेक द कोशेंट सेमी ग्रुप S ओवर रो I, वो किसके बराबर है, यू दैट सेमी ग्रुप यू कैन थिंक ऑफ एज S माइनस I यूनियन 0. Okay, S minus I union 0. So we call this congruence rho I as the Rees congruence. we call rho I as the Rees congruence. REES, Rees, Rees congruence. We call this as a Rees congruence, and if phi from S, from a semigroup S to a semigroup T be a morphism, such that kernel of phi, we know that the kernel of morphism is always a congruence. So if phi from S to T be a morphism such that kernel of phi is a Rees congruence, is a Rees congruence, we say that phi is a Rees morphism. We say that phi is a Rees morphism. I said in the beginning that we don't have a similar satisfactory relationship between ideals and morphisms in case of semigroups. And the same is true for Rees morphisms as well, because we will see that not every morphism is a Rees morphism. Okay. So note that not every morphism is a Rees morphism in case of semigroups, is a Rees morphism. Why? Because groups are also semigroups. Groups are, of course, semigroups. Groups are, of course, semigroups. But not every morphism between non-trivial groups, a morphism between non-trivial groups cannot be a Rees morphism. But a morphism phi from G to H between non-trivial groups cannot be a Rees morphism. Cannot be a Rees morphism. Why it is so? क्योंकि रीज मॉर्फिज्म के लिए इसका कर्नल जो है वो कॉन्ग्रेंस होना चाहिए, रीज कॉन्ग्रेंस. एंड ग्रुप्स हैव नो प्रॉपर आइडियल्स. क्योंकि रीज कॉन्ग्रेंस डिफाइन करने के लिए आपको प्रॉपर आइडियल की जरूरत है. ओके. Since cannot be a Rees morphism, since G has no proper ideals, since G has no proper ideals, and moreover H has no zero element. because groups cannot have zero elements, and H has no zero element. H has no zero element. अगर आप प्रॉपर आइडियल मान लो नहीं, आप अगर आप पूरे G से भी कंस्ट्रक्ट करते हैं, मैंने कहा पहले तो G में कोई प्रॉपर आइडियल नहीं होता। मान लो आप प्रॉपर आइडियल नहीं लेते हैं, आप G ही लेते हैं। G के आइडियल G है और E इटसेल्फ है। तो जब आप G लेंगे तो जो रो आई है, रो आई जो कोशेंट सेमी ग्रुप है एस ओवर रो आई, उसको उसको हमने कहा वो एस माइनस आई यूनियन जीरो होता है। लेकिन जब आप प्रॉपर आइडियल नहीं ले रहे हैं तो जी माइनस जी क्या हो जाएगा, जी माइनस जी इज नथिंग। सो आपके पास ये जीरो आ जाएगा, जीरो। ये जो कोशेंट सेमी ग्रुप एस ओवर रो आई है, इट वुड बिकम जीरो, सॉरी, जी ओवर रो आई, जी ओवर रो जी, जी ओवर रो जी, it would become 0. And since you have a morphism, so the image of phi, the image of 0 under phi, it must be 0 belonging to H. But since H is a group, so it has no zero element. It has no zero element. So not every morphism is a Rees morphism in case of semigroups, because groups are of course semigroups. And if you take any morphism, group homomorphism between non-trivial groups G and H, it cannot be a Rees morphism, because G has no proper ideals and H has no zero element. So, so we shall write S over rho I. To ease the notations, we shall write S over rho I as S over I. S over I, and S over I, and when we shall talk of the kernel of a Rees morphism, we shall mean the ideal rather than the congruence. And when we shall talk of the kernel of a Rees morphism, we shall mean the ideal I. We shall mean the ideal I rather than the congruence rho I. This is just a notation actually, rather than the congruence I, rather than the congruence I. So there is a sort of correspondence theorem in case of rings as well as in case of other, say for example, modules or vector spaces. The similar proposition is also true here. It is elementary, but it is very important. It says that let I be a proper ideal whenever I am taking I be a proper ideal in a semigroup S, it means I am dealing with those semigroups which are not groups. Let I be a proper ideal of a semigroup S. Let I be a proper ideal of a semigroup S. Let A be the set of all ideals of S containing I. A be the set of all ideals of S containing I, and B be the set of ideals of S over I, and this B be the set of ideals of S over I. Then the map theta from A to B defined by theta actually sends any j to j over I. Okay, j belongs to A. Is an inclusion preserving bijection from A to B. Is an inclusion preserving bijection from A to B. Okay, so its proof is just straightforward, because suppose we want to show that theta is 1 1, say theta is 1 1. Bijection means 1 1 on 2. Theta is 1 1. So suppose j1 theta is same as j2 theta. This means j1 over I is same as j2 over I. Okay, so let x belongs to j1. Okay, x belongs to j1. So this means x row I belongs to j1 over row I. j1 by I mean, this is just a notation I have explained here. j1 over row I same as j2 over row I. So this means x must be an element of j2 then. X belongs to j2. So j1 is a subset of j2. Similarly, we can show that j2 is a subset of j1. So this means j1 is same as j2. So theta is 1 1. Now theta is onto. Theta is onto. So to show that theta is onto, to show that